Okay, good morning. So today we're going to learn, this will be our first video on the chain rule. So yeah, let's just get started on that. What is the chain rule? The chain rule is how we take the derivatives of a composite function. Some of you are probably thinking, what's a composite function? Yeah. So like a composite function, I'll give you an example of maybe a more complex one. Might be something like this. How about the square root of x squared plus 3 raised to the 4th power. Okay, that's a composite function. Okay, it's functions inside functions. In fact, you've got x squared plus 3 inside a square root, and then all of that is inside something to the 4th power. You probably did a lot of these back in the day in your pre-calculus and algebra 2 days. So if I were to decompose this function, it might be something like, let's say p of x is x squared plus 3. Q of x is the square root of x, and h of x is equal to x to the 4th. And so this function f is equal to h of g of p of x. If you remember that. Maybe some textbooks you might remember the little circle. The little tiny circle there. Hog op. But yeah, that's a composition of functions. So the question is how do we take the derivative of something like this? Okay? So I'm going to pause, erase the board, and then come back and we'll show you. Okay, so here we are. I got a clean board. Let's learn the chain rule. Normally, in a regular year, I would sort of front load the chain rule. I would teach the chain rule to you as we were going along, and so then when we actually got to the chain rule in the book, you'd be like, oh, I already know how to do this. But it's kind of hard to do that in this setting, so I'm going to kind of try to do with you right now what I would normally do in class, but you're not here to respond. So I'm just going to give you some functions here. So here I'm going to say the sine of 3x. Okay? So the sine of 3x, and I'm going to tell you the derivative of this is the cosine of 3x, which is maybe what you would have expected. But then there's this extra factor of 3 thrown in. So the derivative of sine of 3x is the cosine of 3x times 3. So I want you to be thinking, where's that 3? Why is that there? Okay? So that's our first little example. Before I just tell you the chain rule, I'm going to see if you can kind of discover it as we go along here. Okay, here's another one. New function. How about the sine of x squared? Okay, the sine of x squared. Okay, and I'm going to go ahead and tell you right now that the derivative of this is the cosine of x squared times 2x. Where'd that 2x come from? Where'd that 2x come from? Okay, let's do another one. I keep using f for our rule here, so hopefully you guys can go with it. You want to mix it up and use g or h and knock yourself out. How about x squared plus 4x raised to the 4th power? Okay, x squared plus 4x raised to the 4th power. All right, now you could actually at this point in your life take the derivative of this without the chain rule, but it would involve you actually multiplying out these 4 factors, x squared plus 4x times x squared plus 4x times x squared plus 4x times x squared plus 4x. It'd be like a quadruple FOIL job. Nobody wants to do all that algebra. I mean, come on. I'm going to just go ahead and tell you that the derivative of this, are you ready? Is 4 times x squared plus 4x to the 3rd power times 2x plus 4. Now we could simplify that, but I'm going to leave it like that unsimplified because I think leaving it unsimplified at this point in the game is going to help you figure out what the chain rule is. Let's do another one. How about, I'm going to use g, just so g gets some love. Tangent of x squared. Let me get some ink. G of x is tangent of x squared. What's the derivative of tangent of x squared? You ready? Anybody have an idea what it is? Maybe make a note before I tell you and see if you're right. Secant squared of x squared times 2x. Let's do one more. How about h of x equals the square root of x squared minus 4x? Before I take the derivative of that, I'm going to think of it like that. Maybe you should too. Okay, ready? Maybe you should pause it and try to take this derivative on your own and see if you got it. Maybe you figured out the rule. The derivative of x squared minus 4x raised to the 1/2 power is 1/2 times x squared minus 4x raised to the negative 1/2. But then I'm going to multiply it by something. What am I going to multiply it by? Hopefully you're saying 2x minus 4. Okay? So the question is when I'm taking the derivatives of these things, what is it that I'm multiplying by each time? Like right here. It's me. What is that 3 there? What is this 2x there? What was this 2x plus 4 there? What was that 2x there? What's this 2x minus 4 here? What is that? There's something popped up on my screen, so I'm getting rid of it. What are these things that I'm multiplying by? Well, hopefully you're saying it's the derivative of what's inside. So like right here, 3x, the derivative of 3x, 3. Right here, the derivative of x squared, 2x. Right here, the derivative of x squared plus 4x, 2x plus 4. Right here, the derivative of x squared, 2x. Right here, the derivative of x squared minus 4x, 2x minus 4. So it's like you treat this like you just take its regular derivative. You want to look at this sine function. What's the derivative of a sine function? It's a cosine function. And then multiply by the derivative of the inside. Oh, you got this thing raised to the 4th power. What's the derivative of something to the 4th power? Oh, it's 4 something to the cubed times the derivative of the inside. Oh, what's the derivative of a tangent function? It's secant squared times the derivative of the inside. Okay? So I'm going to erase the board here. We'll state this formally a couple different ways, and then we'll do some more examples. Okay. Oh, sorry. We're back. So the chain rule formally stated. Okay, that definitely deserves a smiley face. The chain rule formally stated is this. If y equals f of g of x, that's a composition of functions. dy dx equals, maybe you should try to state it, f prime of g of x times g prime of x. Okay? In a minute, we'll break down one of these and show you how that works, just so you can see it. But we won't necessarily write it out this way every time. Okay? Another way that we can think about the chain rule, and this will come up in a little bit further discussion when we get into some application. If y is a function of u, and you don't have to use u here, you could use other variables, and u is a function of x. Actually, let's use t here just to mix it up. If u is a function of t, then dy dt, the derivative of y with respect to t, is equal to dy du times du dt. Okay? Now, I'm going to explain this in kind of in words to try to make this second way make a little bit more sense. We will use this method a lot more, this way of thinking about it a lot more, like I said, when we get to some application problems. But let's say you've got something that's a function of u. Maybe u is height, and then that height is a function of time. So maybe y represents area, is a function of height, and the height is changing with time. What this is actually saying is what would your area, how's your area changing with respect to time? Well, you first find out how your area is changing with respect to height, and then multiply that by how your height is changing with respect to time. Okay? It's this way is really a way when we can kind of deal with functions of two variables, but not really deal with functions of two variables. We like secretly deal with functions of two variables. So this is this notation. This is I keep sneaking this in here. This is the Leibniz notation, named after Wilhelm Gottfried Leibniz, German mathematician, one of the co-founders, co-discoverers of calculus. But Newton gets more love, apparently. So let's rate this. We're going to do some more examples. I'm gonna give you an example and break it down to show you how this definition works. But we're not going to break them down every time. We're just going to do them. So we'll be right back. Okay, so we're back. I got a clean board here. Now we're just going to bust out with some examples. So let's say y is equal to, let's make something up here. How about sine of x squared? Now, more than likely, that's not how the problem would be presented to you. It probably would be presented to you like that. Of course, then we're going to think of it as sine of x squared. Okay? So what I'm going to do is I'm going to break this down and say, okay, this is a composition of two functions. The outside function is the squaring function, and then what's getting squared? The sine function. So back in pre-calculus days, if you remember, you had to decompose these functions. So you would have written y as f of g of x. Is that true? Like, this is f of g of x means take g and f it. So take g and f it would give us that, right? So according to the chain rule, what we just said was that dy dx is f prime of g of x times g prime of x, right? So right here, tell me what f prime is. F prime of x is 2x, right? And then right here, tell me what g prime of x is. G prime of x is cosine of x, right? So now, if I use this rule, it says take f prime of g of x, which means take g and f prime it. So take g and f prime it. So that's going to be 2 times sine of x, right? And now we're going to multiply that by g prime, which is cosine of x. So there's our answer, 2 sine of x times cosine of x. Okay? Now, I don't go through this whole process each time because after you do a few of these, you can kind of just start to see it. Like you'll see that's the inside, the sine of x is the inside, and then what's happening to that? It's all getting squared. So when I do this, and you will too, you're just going to look at this and say, oh, it's the derivative of the whole thing. 2 times sine of x to the first. Then multiply by the derivative of the inside. And what's the derivative of sine of x? Cosine of x. Okay? So it's just a little bit of a quicker way to go about doing it. You take the derivative of the whole thing, and then you multiply by the derivative of the inside. Okay? Let's do another example. I'll pause. Oh, we're back. So here we got a function, secant of x squared plus 2x. Okay, and we're going to use the chain rule to take the derivative of this. Okay, so first, before you jump in there, think about what's the inside function. Like, you have x squared plus 2x. Yeah, it's what's inside the parentheses, but that's not necessarily always the best way to go about doing it. But I got x squared plus 2x here. That's on the inside. And what's happening to x squared plus 2x? It's getting secanted. If that's a word. If that is secanted, is that a verb? Okay, I guess it is now. Okay, so it's getting secanted. Okay, so we're going to take the derivative of this. So we're going to take the derivative of the whole thing. So you have to think, what's the derivative of secant? Of secant of something? Well, it's secant of the something, tangent of the something. Okay, so that's the derivative of the whole thing. And then we're going to multiply by the derivative of the something. So what's the derivative of the inside? 2x plus 2. Okay? Derivative of the whole thing times the derivative of the inside. So that's an example. Let's try another one. You can see this opens up the door big time for different types of functions that we can take the derivative of. So how about tangent of sine of x? Tangent of sine of x. What's the derivative? What's the derivative of tangent of sine of x? Well, you have to think, okay, what's the derivative of the tangent function? Hopefully by now, you're getting kind of good at those trig functions because you're going to have to know them. You got to know the derivatives of those trig functions like that. Okay? What's the derivative of the tangent function? It's secant squared. So the derivative of tangent of something is going to be secant squared of the something. Then times or multiplied by the derivative of that something, which is going to be cosine of x. So that right there is the derivative of tangent of sine of x. Okay, so let's do another one here. Okay, I wore my blue jacket here so you can see when I write, you can still see it. Let's see. Let's go back to F. Ready? Here we go. How about this? Let's do it like this. Here we go. Sine cubed of 2x. The first thing we're going to do is we're going to rewrite that as sine of 2x cubed. Okay? And now hopefully you might be freaking out. In fact, I'm kind of hoping you're looking at this and saying, whoa, I don't know about this. Because what's going on here? What's going on here that wasn't going on before is now we've got an inside of an inside. We've got something to the cubed power, right? But then that something that is getting cubed is itself a composition of functions. It's like chainception, okay? So how do we take the derivative of that? Same way. It's actually real simple. We still just take the derivative of the whole thing. So we treat this, okay? 3 times sine of 2x squared. So that's the derivative of the whole thing. And now we're going to multiply by the derivative of the inside. So now, when I look at this, I've got to take the derivative of sine of 2x. Just sine of 2x. So what's the derivative of just sine of 2x? What's the derivative of sine of something? It's cosine of something times the derivative of the inside, 2. Okay? And I'm going to purposefully leave this unsimplified. Yes, I can multiply the 3 and the 2 and get 6, but I'm going to purposefully leave this unsimplified so you can see the various parts that sort of popped out of here. Okay? In fact, I'm underlining these in color so you can see. This right here matches up with the derivative of sine of 2x. This right here is the derivative of the 2. Okay? So you take the derivative of the whole thing times the derivative of the inside, but if the derivative of the inside is a chain rule, you take the derivative of it as a whole thing, then times the derivative of the inside of the inside. Yeah, okay? You'll get it, trust me. It just takes some practice. Okay, let's erase. Okay, so got another example here. This looks ugly, man. Oh, h of x is x squared plus 2x over 3x plus 1, all of that raised to the 5th power. Okay, so we're going to chain this baby up. Okay, take the derivative of this sucker. Okay, so how do we do this? We've got something to the 5th power. So we're going to take the derivative of the whole thing. It's like you just treat the something like it's an x. So that's the derivative of the whole thing. Now we're going to multiply by the derivative of the inside. Ooh, how are we going to take the derivative of the inside? We're going to have to use the quotient rule. That's right. Okay, so here we go. Low d high minus high d low over low squared. Okay, so this is the derivative of this function. The chain rule often makes derivatives look more complicated. Okay, now do you want to simplify this? No, we don't want to simplify this. This is like horribly ugly. Okay, horribly ugly to like middle school yearbook ugly. I mean, that's horrendous. Okay, let's do another one. Let's use a fat marker this time. How about f of x is how about you guys try this one? Square root of let's just do square root of sine of 3x squared. Okay, the square root of sine of 3x squared. Let's take the derivative of that baby. What's the first thing we're going to do to this? Okay, we all think of this as sine of 3x squared raised to the 1/2 power. Okay, we got to think of that first. All right, now we're going to take the derivative. Maybe you should try this one on your own. Pause the video. See how you do. Ready? Here we go. Derivative of the whole thing. Times the derivative of the inside. Now the derivative of sine of 3x squared is going to be cosine of 3x squared times the derivative of the 3x squared. 6x. Okay? And there we go. That's the derivative. Leave these unsimplified. It's actually easier right now for you to leave these unsimplified because you can see the pieces. I think I've already said that before. It also is easier for me to grade if I was actually grading them. And good news is if I give you a quiz and something in Delta Math, when you're doing this in Delta Math, you can leave them like this, or you can simplify them and it counts it right either way. Okay, I'm going to pause this. We're going to do one more thing, and then I'm going to turn you loose. Okay, so while we were working out those last few examples here, I decided let's actually work out an example where we use that Leibniz notation, and it's just sort of so it'll make a little bit more sense for you. Okay, and I'm actually going to start off with some things that maybe you're familiar with. Okay, so here's a function. I'm saying a equals pi r squared. Hopefully you realize that that's the formula for the area of a circle. So the area right now is a function of the radius, right? Everybody knows that. Okay, but I'm going to tell you, for some reason, I don't know why, the radius is now a function of time. Okay, for whatever reason, the radius is changing with respect to time. Like, you know, at t equals 2, the radius might be 4 times 2 plus 2, which is 10. At t equals 10, the radius is 4 times 10 plus 2, which is 42. Okay, so the radius is changing. It's not constant. What that makes kind of deciding what the area is doing is, it makes that weird, right? No longer is the area just pi r squared. Like, we have to take into consideration that the radius is changing, right? So I'm asking you, what's dA dt? Okay? Well, dA dt is going to equal dA dr times dr dt. Okay? So it's very simple, all right? So what do we do? We're going to say, all right, well, what's dA dr? What's the derivative of the radius with respect to r? How is the area... I just said, what's the derivative of the radius? Idiot. What is the derivative of the area with respect to the radius? How is the area changing with respect to the radius? Well, dA dr is, well, pi just hangs, right? And then times 2r, because constants hang. So that's dA dr. So right down here, I'm going to say I'm going to rearrange that and put 2 pi r. Okay? Now what's dr dt? How's the radius, what's the rate of change of the radius with respect to time? What's dr dt here? It's 4, right? That's a linear function there. So down here, I'm going to say times 4. Okay? Now, I could leave it like this, or I could go back and resubstitute what r was. It was 4t plus 1. Or I could have just left it like this, okay? So this is another way that we'll use the chain rule, okay? I don't think you're going to have any problems like this right out of the gate, but I did want at least to front load this to you and just let you kind of see what's going on here, how the chain rule is useful when we're dealing with functions of, that are composed, but the variable might change. Like here, where you have area in terms of radius, but radius is in terms of t, or time. Okay? So I'm going to leave you some problems to do. Well, actually, I'll write them down for you right now. This is from section 3.6 from your book, right? So that's 215, 217, 228 to 237. This is just a bunch of practice type problems. And then 245 to 251 odd. Okay, this is going to be problems where you're doing the chain rule, but the functions are given to you as a table of values. We'll probably end up answering some questions on those, but these are the kinds of problems I'd like you to sort of have a little bit of a productive struggle with. And then we'll come back and talk about those probably in the next video or in the next class. So that's the chain rule, at least first go around. Hope you enjoy that, and yeah, we'll see you soon.